Welcome everybody to our next lecture regarding the feed-forward control. In this lecture we want to talk about the problems with the classic feedback control. So as you might know, we have a system, a chemical process for example, we want to control. You have some input variables, some output variables, and the inner state variables which we want to change in order to create the behavior we like. And we have, of course, disturbances which try to upset the inner state of the system, so we have to work against that. The classic, or not only the classic, but the most known approach is to use a so-called feedback loop. So we measure some output variables, here the green, the measured outputs, and then we feed these measurements back to our inputs, and we change our inputs accordingly. So here we close the so-called feedback loop with this feedback. So what is the advantage of this approach? Why is it so often used? The advantages are as following. The first big advantage is that it works really well for set point changes. So in other words, when I try to change the state of the system, I can change my input, and then I measure the output, and then I feed it back into my into my inputs, and then I can really well control some kind of input or set points that I set for the system. Another big advantage is that the structure and also the hardware I need for this is actually quite simple and cheap, so therefore it's very widely used. So we can note here that it is simple to implement. It is simple to implement and therefore widely used. But of course, these kind of systems not only have advantages but also disadvantages, and these are the reasons why we are looking into the system, so in order to understand what are the trade-offs we are dealing here with. And so we will start a new section, the disadvantages. So, and what kind of disadvantages do we have here? In order to demonstrate it, I will draw a little diagram for you. Here we have, on the x-axis, we have the time t. And then on the y-axis, we have some kind of different variables. For example, a set point. So we want to have a system in a certain state, which is marked in green here. So this is our set point. And then we have some kind of disturbance, so some kind of random effect, which is at the beginning has a value of 0, and then at some point in time it jumps to another value. Then it stays the same. So how is our typical reaction? So first of all, we noted here the disturbance. How would our system typically in such kind of feedback system react in response to such a disturbance? At the beginning it would be at our set point, and then when the disturbance starts, for example, it would go up our value, then the feedback control would realize, oh no, we are leaving our set point, and then it would correct the system. Then it might be a little bit overshooting, and then you would have a system which is again near our target value, so near our set point. So this one here is the output of our system. And here we already can see the problem with this kind of control approach, because we have this disturbance here, and for this time period here, so probably until here, so during this time frame, our system is not at our ideal state, not at our set point. Here in this part, its value is too high. Here it's too low, and then here it starts to have the value of our set point again. And this is actually one of the biggest disadvantages of a feedback system, which is that the disturbance first has actually to disturb our system, and then we measure the disturbance and react to it. So with a feedback system, we can't avoid the disturbance, we just can detect it, and then we can correct for it. So we can note here, the disturbances first must change the process outputs. And then when these process outputs are changed, then we can measure it, and then we can correct against these disturbances. So we can note that they change the process outputs, and then the corrective control action will be taken. The disadvantage here is that in the time between the changed process output and the moment we correct in our control system for this disturbance, in the meantime, so in this time frame, our system might be in a suboptimal position, and maybe it's also a dangerous place. So you could imagine that if this is, for example, a temperature scale here, that maybe the system has some kind of critical value. And if our system is too slow, then we maybe overshoot this critical value and have a kind of system which might be explosive or has some other kind of problematic properties. Therefore, the big disadvantage here is that we correct for the disturbance, but maybe it's already too late. So this is the big problem here, because we may be too late. Yes, what can we do about it? I mean, we see here that we have this disturbance. The disturbance affects our system, and then we react afterwards. The idea how we could avoid this kind of problem is that we measure the disturbance in the moment it enters the system, not when the disturbance leaves our system through the output variables. So that we are just faster than the disturbance, or at least as fast as the disturbance, so that we don't lose the time between the disturbance disturbs our process, then it changes the outputs, and then we feed it back, and then we adjust our input variables. So the idea here is we use the so-called feed-forward control. And the idea with the feed-forward control is that we measure the disturbances while they are entering the system, not when they are leaving the system. So how this actually works, we will see in the next video. And with that note, I will say thank you for listening and see you in the next video.